Okay, folks, this is about buffers, 7.3. So what is a buffer? Well, a buffer is a solution that resists changes in pH, and proteins and DNA must be set in buffers in order for them to maintain their structure and function. Changes in pH can add or subtract charged ions from them. So buffers resist changes in pH because they contain molecules that react with hydrogen ions and hydroxide ions in solutions. So you can have buffers that are either a weak acid and its conjugate base, like carbonic acid or acetate buffers, or a weak base and its conjugate acid, like tris, like a tris buffer. So there's a carbonic bicarbonate buffer system in our blood. So it is one of the major buffering systems that is used to maintain the pH of mammalian blood. So it's used in the formation of acid and lumen on the stomach, in the stomach. It's used to neutralize the pH of the chyme leaving the stomach and entering the small intestine. So how it works, there's a little figure 7.16 on page 204 of your book at home there. So the buffer is composed of a weak acid and its conjugate base. When a small amount of carbonic acid, which is carbon dioxide and water in red blood cells, we know coming out of us, respiration here, is added to, in our circulatory system, is added to a bicarbonate buffer, the acid ionizes to release hydrogen ions, which would decrease the pH if they were not bound by the conjugate acid in the buffer. So, I'm sorry, and its conjugate base, I apologize, and its conjugate base in its buffer. So it's maintaining the pH of our blood, basically. This buffer system is so important, of course, for us to live, that keeps our pH neutral and relatively neutral in our blood. Okay, then in biotech, we've been working with a lot of this. We've been working with buffers, and we use buffers for DNA, gel electrophoresis, phage gels. We also use it to store proteins and whatnot. So you've worked with TAE buffers, TE buffers, TBE buffers, sodium phosphate buffers, what have you. So there are acetate and then there's tris buffers. So an acetate would be for protein purification. The that A in the TAE buffer is acetate. So acetate would be for protein purification. It has a weak acid in its conjugate base. The acids bind to excess hydroxide ions in solution while the protein is processed. Now, tris is used in DNA storage. We'd use TAES or TE. When you were in biotech too, the first thing you did was put together a TE buffer, which was tris and EDTA. So those two solids were put together in a beaker, and then you had to bring it up to 100 milliliters, and then you went ahead and you mixed it up and you set up the pH. So that's used for DNA storage because you were doing DNA extractions in biotech too at the beginning. So tris is used in DNA storage. It has a weak base and it's conjugate acid. It maintains the pH between 7 and 9. It accepts or releases excess hydrogen hydroxide ions in solution. Okay, so some ideas here are some concepts that go along with buffers, and I always call it the buffer bonanza because I always give like a little matching about these two ideas here, PI and PK or pKa. So selected mainly for the final pH that they provide in solution. So with what's PI is, and I mentioned this, we talked about protein structure a little bit. We're talking about amino acids and polypeptide chain and the positive negative charges on amino acids. That's like this. This is what this is. PI is called isoelectric point. You can look it up for proteins. And it's the pH. So it's a pH value where the positive and negative charges within a protein are equal and cancel out so the protein is electrically neutral. So when the pH of the solution equals the protein's isoelectric point, the protein itself will just fall out of solution. Because that's it. That's how it goes, because that's where the positive and negative charges within a protein are equal, and it would cancel out. So the protein's just going to be neutral. It's going to fall out. That's not good if you're trying to store your protein. What you want to do is for storage and to maintain it being in solution, you want your protein to be you want the solution to be about 1 to 2 pH units from the protein's PI. That's what you want. You want, if you're looking at the PI of the protein, say it's 6, you want your solution buffer that it's being stored in to be about 1 or 2 units off from it. So that's important. We'll go over that in the review. Okay, so PK or pKa, and this has to do with the buffer. This is the property of the buffer. It's the pH at which 50% of the buffering molecules dissociate or ionize. So when pH equals the pKa, the buffer has its highest buffering capacity. Okay. So there's a table there about buffering agent name, pKa, buffering range, examples in the first application only. So we look at cellulase. So cellulase, you got that thing where, okay, you look for the PI of cellulase, like 6.5, and then you think, oh, well, maybe it was 4.5. I got to remember here. On cellulase, let's look it up in the section here in the book. So for cellulase, I'm just going to look it up. Basically go with it, basically on this page 206, the table. So if you look at cellulase, depending on its source, cellulase has a PI around 4.5. So that's what you would look up. So you need a buffer that would be good for cellulase. You'd want to make it about 6.5. Again, that's 2 pH points away from its PI because then it won't fall out of solution. Okay, so then you look at the table 7.2 and you look for something that has a pKa around 6.5. And which one is it? Oh, it's going to be potassium phosphate. It has a pKa of 6.82. Okay, so the closer the pH of the buffer is to the pKa of the weak acid, the better its buffering capacity. So potassium phosphate and dipotassium phosphate are usually good to generate buffers of pH values around 6 to 7. So this would be a great one for cellulase. So this is a good one to use for cellulase. So that's how you pick them out. That's how you would pick out your buffers. Okay, and how to make a buffer. This is something you've been doing a few times now in biotech. You find out using the molarity concentration equation, finding out how much mass of buffer that you have to weigh out. You know, what molarity are you making it? What's your molarity of your buffer? With TE, I remember you would have to find out what mass of T and what mass of E, what mass of tris and what mass of EDTA do I have to put together based on its molecular weight and the molarity, because I think both were like 50 millimolar or 5 millimolar, and then you would put it up to 100 milliliters of water. So you would do your calculations to find out what grams to put in your beaker. Then I had you guys put it up to, or Miss Lehner, we put it up to 75% of volume desired. So you would just put it up to 75 mils if it's 100 mil at the end. Its final volume is 100 mil. Then before you add the last 25 mils of water, you want to adjust the pH to what is desired, and that would be using the whole situation with the ring stand. And I have that all, I'm going to set that up to see that. The ring stand with the spinner and your beaker and the spin bar, and it's spinning, dilute, it's dissolving it all the way through. Then you put your pH meter in there and you've set it and you've calibrated it. Then you're noting whether it's pH of 6 or 7. If it's pH of 7 and you got pH of 5, you want to bring it up with sodium hydroxide. If it's the desired pH is of 8 and you need to bring it to 4, then you're going to add hydrochloric acid to it. After that's done, then bring up the rest of the water up to 100% of the volume of buffer desired. So if it's 100, then you put the other 25 mils of water in there, and you're all set. Okay, so application of buffers in biotech. Use it as a solvent for protein nucleic acid solutions. Use it as an ingredient to risk pH changes in cell culture. Use it as a liquid phase in column chromatography, which I have to do with you later in chapter 9. And then use it as a liquid for conducting electricity in a gel box, which we use a lot. Okay, let me move through here and do this thing called buffer bonanza. It's kind of a cute little thing here. There it is, buffer bonanza. That came up a few years ago. It's all these multiple choice question things are matching for it. Now, okay, so let's go back. So PI is called the isoelectric point of protein being stored in buffer solution. Now that's what you find for the protein. It's because it's the amino acid sequence, and whether it's got a certain charge or not, that's the gist of it. And then whatever it's in is the isoelectric point. So that's as far as I'm going right now on this. So then you want to make sure that when you're picking out your buffer, you look for a buffer that has a pKa that is about 1 to 2 units away from the protein's PI. And again, that's it. So to find PI of an amino acid, if you had to, you would have to average the pKas of the side groups of amino acids to make up your protein. So you could do that if you had to from scratch, if you couldn't find the PI of the actual protein itself. Okay, so pKa tells how acidic or not a given hydrogen atom in a molecule is. pH tells how acidic a solution is. So pKa is that pH at which, again, 50% of a buffering molecule in aqueous solution is ionized to a weak acid in its conjugate base, equal to number of neutral and ionized units. Strongest acid has a pKa of negative 10, weakest acid pKa of 50. So again, it's that thing where, for us, it's to set the pH of a buffer equal to the buffering solute's pKa value. Make sure you have the best buffering capacity. So, but if you're putting a protein in a buffer, you look at the PI of the protein, go up probably going up 2 points up, 2 points up on pH, and then find your buffer that has that pK that equals that. That's the gist of it. Okay, that's it. So now I'll move on to 7.4, 7.5 in the next presentation.